To talk about any kind of motion, we always need to consider displacement, velocity, and acceleration. We can think about displacement as a position vector function of time. Any point on the curve can be given by the position vector. We can assign a function f of t to be the displacement in the x direction, and we can assign a function g of t to be the displacement in the y direction. Together they will form the position vector r. We can now think about tiny changes in the input of the position vector. This will allow us to define the derivative. As we can see, the derivative of the position vector is just the derivative of its entries. Since velocity is the rate of change of displacement, we can take the derivative of r to find the velocity. Note that the velocity is always tangent to the path. We can use the same idea to get an equation for acceleration, since it is the rate of change of velocity. These ideas will be key to helping us understand and, more importantly, derive formulas for circular motion. Consider a circle. The displacement is always the radius r. The velocity is always tangent to the circumference. The change in the direction of the velocity points opposite to the displacement. What we can do is start by coming up with a position vector for the circle. To talk about any point on the circle, we can consider its distance from the origin and its angle with the x-axis. We can then get a function for the x displacement, and similarly we can get a function for the y displacement. We can then put them together to get a position vector for the circle. However, to get any sense of velocity or acceleration, we need r to be a function of time. We can achieve this by using the angular velocity formula. Using our rules from before, we can find the acceleration and velocity vectors. When we have a closer look at the acceleration equation, we can see that by pulling out the factor of negative omega squared, we get a relationship between the acceleration and displacement. Particularly, the acceleration points in the opposite direction to the displacement. If we take the modulus of both sides, we arrive at the centripetal acceleration. We can then use this in conjunction with Newton's second law to get a formula for the centripetal force. A key insight is that the maths we have done up until this point completely agrees with the force diagram we drew. Since the centripetal acceleration points towards the center, we can also see that the centripetal force points into the center as well. This is a key property of circular motion. A quick recap. The centripetal force and acceleration both point towards the center of the circle, and we have derived the formulas for both. However, it's important to also calculate these quantities based on the speed of an object, not just their angular velocities. Consider this setup. Any movement on the circumference can be linked to movement in a straight line. The distances dc and d are equal. And we can write a formula relating dc and the angle. We can then arrive at the equation v equals omega r, which relates the angular speed to the linear speed. We can then use this formula to rewrite the centripetal acceleration in terms of linear speed. Using this new acceleration formula, we can also rewrite the centripetal force. And this is the equation at the heart of circular motion. Thank you for watching this video.